So what we're going to do today is I'm going to give you essentially an overview of the course in 28 slides. In terms of the content of the course, right? I did like just overviews before. This is the most sort of linear presentation that will happen during the quarter. That being said, I encourage you to ask questions while I'm going along. Right? So this doesn't have to be a 28-minute presentation of 28 slides. All good? Alright, so who can restate the relatively concise definition that I gave of the global warming paradox on Tuesday? Why is class called the global warming paradox? Yeah.
The most straightforward way, or like the seemingly easiest way to raise like well-being is to raise energy consumption. But raising energy consumption is going to raise the CO2 emissions, which could lead to more global warming.
So we just like to add into that definition, is that the people most affected by climate change are the people who most need increased like energy resources consumption.
Exactly. So this is key to it being a paradox, is that in the current climate, there are billions of people who are tremendously exposed to climate stresses in the current climate, right, without any climate change. And the paradox is that for those very large populations, they can decrease their vulnerability to climate stresses by increasing energy consumption, which will increase climate stresses, even though their vulnerability will be decreased. So that's the paradox. So both of these are correct. Okay. So I'm going to give you the 45-minute version of why that's true, and then we're going to spend the rest of the quarter doing what will be a 9-week version of why that's true. Right? Okay. So has anyone seen this picture before? Has anyone? All right, well, let's do this. Take 30 seconds to discuss with your table. So if you think this is a picture of.
Under like the street lights.
Got quiet for some reason? Does that mean you're done, or are you?
Yeah, just looking.
So I guess they don't have power in their homes.
All right. Anyone want to give their conclusion of what this is a picture of? Yeah, Sean.
People are using street lights to do homework because they don't have power or a light.
That is exactly right. So this picture was taken, I think, in 2008 by Andy Revkin. It's in the Republic of Guinea in Africa. This is the airport in the capital. And these are college students who do not have electricity in their homes. And there is this phenomenon of this migration, this daily migration in the evening to the airport, so that students can study underneath the lights on the side of the road at the airport. Right, so in the most fundamental sense, we're here at a university. The most fundamental vehicle for increased human well-being, human capacity, education, right? That depends on energy.
Sorry.
I'm sorry. Just want to make sure I wasn't being disrupted. So there's lots to talk about in this photo. Gender dynamics, right? There's a lot reflected in the photo, but the in terms of the core challenge of increasing human well-being, even being able to study throughout the day, right? Extending the day, extending the time available to study. This depends on access to electricity. Right? So this is a really critical reminder of how important energy resources are. And as I said on Tuesday, like, climate change is really a side effect of something that gives all of us and huge populations of people around the world great benefit, which is fossil fuels. All right, and so your generation is facing a huge challenge over the next few decades, right? So, you know, by the middle of this century, there are several imperatives, which we'll talk about, to increase energy supply and access, increase the total energy supply globally, and increase access, right? So not just increase supply proportional to current access, but to expand access. To decarbonize the global energy system, this is what the UN Paris Agreement has committed to. And simultaneously adapt to continuing climate change. And as will motivate over the rest of today, each one of these three is a huge challenge individually. And doing all three simultaneously is a much larger challenge than any of the three individually, or all three individually. Doing them simultaneously is a huge challenge. All right, so first, why am I arguing that over the next 30 to 50 years, we will have to increase energy supply and access globally? So the primary reason is energy poverty and the very large populations of people globally that do not have access to modern energy resources. So energy consumption brings tremendous benefits, right? We're benefiting right now in fundamental ways, right? Luxury benefits, but also fundamental benefits for survival. Right? So there are about 1 billion people without access to clean drinking water globally, and that definition of clean is a very forgiving definition of clean. So if we walked up to the water that the 2nd billion have access to, we would be unlikely to drink it, right? So this is 1 billion without clean water is like a really, really dirty definition of clean, right? And then there's another billion who have access to not as polluted water, but still not water that we would consider clean in any urban area in the United States. So there's really like 2 billion people without access to water that we would consider to be consumable. Cooking, 2.5 billion people rely on biomass for cooking. So wood, dung, mostly indoor in small enclosed spaces. Does anyone know what the leading burden of morbidity and mortality is for environmental pollution globally?
Indoor air pollution.
Yeah. So it's air quality overall globally. Air quality is the leading burden of disease for environmental pollution globally, and the largest fraction of that is people cooking in an enclosed space using biomass. And so there are millions of people a year getting sick and dying from cooking, and using biomass because they don't have access to a cleaner heat source for cooking. Illumination, right? So about 1.5 billion people without reliable access to electricity. There's a lot of really innovative work going on in terms of decreasing, there are people trying to decrease all of these, but certainly with electricity with rooftop solar, this number is going down as a result of rooftop solar. But lack of illumination is still a huge barrier to human development. Transportation, huge populations that don't have access to transportation. There's a huge opportunity cost and caloric cost that comes from that. So this is a picture from the IPCC. These are women and girls in East Africa carrying water. Jenna Davis, whose office is, I think that one right there. It's a closed door, not the open door, but closed door. So Jenna Davis, yeah, it's got the decorated toilet outside of it. Yeah, so she works on sanitation and development. They've got the decorated toilet growing a plant. So she has worked in East Africa and elsewhere, Bangladesh and elsewhere around the world. But she has research from East Africa, where this photo was taken, quantifying the hours per day that women spend fetching water. So I'm going to take 60 seconds. I want you to talk at your tables, and at the end of 60 seconds, you're going to each take a stand. You're going to make a prediction about what Professor Davis's results show. So the question for you is, what is the average hours per day? So the mean hours per day spent fetching water. Yeah, fetching is the word that Jenna uses. So gathering water. So this is going, getting, returning. Discuss for 60 seconds. You make a prediction. Put on board where you all can see it. Yeah, maybe it's more.
I feel like, and depending on how many trips you make, like if you're assuming that you can't carry, like water is heavy, you can't carry them.
I don't remember because I feel like I'm almost putting like water.
You can hear everyone talking.
I think it's really
Yeah.
Because I feel like we need a good 7.
Yeah. It doesn't happen
Seven's always a good number.
All right, 15 seconds for you to settle on your prediction. You can have multiple predictions from the table. You don't have to agree on a prediction.
Alright, well, I'm 60.
All right, who's got a prediction? Jenna's done the research. She's been to East Africa. She's gathered the data. Camille.
Say 11.
All right.
8, 7.
Yeah, we're
7.
Yeah.
10.
Well, alright, Jenna's research finds that the average hours per day in East Africa, I think in Tanzania was where she's doing research, gathering water, 6 hours per day. Which is lower than all of your predictions, but is still a lot of the day. Right? So if you imagine the time spent, right, just the opportunity cost.
That's every day, so it's like a full-time job, basically, if you're doing that 7 times a week.
Yeah, it's basically a primary activity, and not, you know, it's not a 100% overlap with electricity. But if you imagine also not having electricity in your home, and you also imagine potentially cooking with biomass, and you're in an enclosed space where you live, right, these are multiple risk factors. Yeah.
Is this like one trip or multiple trips?
This is the amount of time in a day on average spent in the water gathering activity. So it depends where the water source is and where the person lives. I'd make an appointment to see Jenna if you want to know about the research. Office right there. A large fraction of time and calories. Jenna's group has done some calculations of the caloric cost as well. All right, and the last on this list, the one that I work on most directly, is vulnerability to climate stresses, right? So the lack of access to energy resources creates tremendous vulnerability to heat waves, droughts, floods. It's not just energy resources, right? There are lots of other risk factors when it comes to climate stresses, but most of the ways that we as humans decrease our vulnerability to climate stresses, right, protect ourselves from the climate system, require energy resources, whether it's seawalls or more heavily engineered structures, houses and buildings, backup generators when the power's out, right? There's just a huge amount of energy that goes into protecting ourselves from climate stresses. And as we've discussed already, that's like kind of the core of the global warming paradox. So you can infer from these statistics that energy is required for human development, human well-being. How does that look statistically? So we're going to hammer away at the missive all throughout the quarter that the correlation does not imply causation, right? So you're going to get plenty of opportunity to think carefully about causation. So there's nothing about causation here. This is just a plot of two variables. So on the x-axis is the per capita energy consumption. This is in exajoules per million people. So if you think about your amount of storage on your computing device, right? You've got kilobytes, megabytes, gigabytes, terabytes, petabytes. I don't think there's an exabyte storage system yet. Right, so that's like 10 to the billion is 10 to the 9, trillion is 10 to the 12. 18? It's like 10 to 18 joules. It's a lot of energy. And then on the vertical axis is the Human Development Index. So this is the UN Development Program has this index of human development. This is not just money. It's not just per capita income or per capita GDP. This also includes like literacy rates and morbidity and mortality rates, child mortality rates, maternal mortality rates. So there's a lot of indicators that go into this one indicator. So I would like you to talk again in your groups, and I'd like you to come up with 3 observations about this plot.
First thing,
And you should talk out loud. So
Energy
you can-
consumption yeah, well-being.
And like there's like a general trend that like you said, increases like that's like wrong, but that's not always true. Like some of them fall pretty low. Like the ones at like 0.1 exajoules per million people is still at like 0.5.
Like there's such a difference.
Yeah, like in the beginning, you want energy to get better, then after a while.
Like the one on the far right, like less efficient.
Yeah.
It's like at the same level as others, but it's.
All right, another 15 seconds.
I'm sure it's not. Yeah, but I bet it's the US.
All right.
Like a steep curve, like it doesn't take that
What's
much
one observation about this plot?
to increase.
I heard a lot of migrants talking. So. Yes. Nate.
There's like the vertical where like the use, like consumption of energy stop mattering towards your human development.
Okay, so it basically asymptotes, right? There's this saturation where increasing, right, marginal increases in energy consumption create no gain in the human development index. Okay, very good. What else? Yeah, Sean.
Energy consumption doesn't always like indicate like where like a country will fall in the human development index. So like there are some like outliers that have much larger energy consumption but still fall pretty low on the human development index.
Yeah, so for a given human development index, there is a range of energy consumptions, and at a given energy consumption, there's a range of HDI values. So there's some scatter. What's the basic shape if you just sort of infer? Okay, so this shape, right? So it's logarithmic, right? You get what? Yeah. Okay. What's one more observation? Yeah. Sarah.
The majority of the countries are like 0.1 or less of per capita energy consumption.
Yeah, so you have a large fraction of the total countries, I'm sure what the diamonds are inside this box here, right? The, less than 0.9 on the Human Development Index and less than 0.2. This is actually Japan's value, is why that dotted line is there. Right, so a large fraction of the countries are below 0.2, and as you point out, even below 0.1. So what fraction, just because I happen to know the number, I calculated it, what fraction of, well, how many people, say there's 7 billion people in the world when this plot was made, how many of those 7 billion people do you think are in these countries that are inside this box? Just no reason you would know, you don't have data, but based on how many countries there are and what you know about population, yeah, okay, I think that's, I'm going to do a quick calculation here. I know the number, but not the percentage. All right, real quick, hold on. It's actually like 85.7%. Oh, it says it right there. All right. Yeah.
I just looked at 15% of global population.
Yeah, so it's 6 billion people. This will happen often, by the way. During class, I'll be asking you a question that turns out is written on the screen. Yeah, so 6 billion people are below this this threshold. Yeah, Japan's level. Yeah.
Do you have any idea like where the United States falls in this number?
I do. We are right, or one of these. Yeah. This is Luxembourg, and Luxembourg's really small, right? It's like basically a bedroom community, yeah, it's basically a city. And one of the reviewers said in their review that Luxembourg should be removed from the analysis, parentheses, and spelled correctly. So I apparently didn't spell it. At any rate, so yeah, we are, some countries are big, some countries are small. We are, well, we're going to see it in a second where we are. Yeah, so if we just add it up, 15% of the global population accounts historically for 85% of the global CO2 emissions, right? And we're only 2/3 of the global GDP. So you can't even make the argument that, well, it's not about population, it's about economic activity. Certainly, economic activity is the primary driver, the primary indicator of the distribution of emissions historically, but it's not proportionally distributed. Right? This is not simply proportional to economic activity, and you have already identified that in different words, right? Because you've said that out here we have really high per capita energy consumption with no fundamental benefit to human development. And I have an anecdote that I think of that helps to explain this, although it's a little less potent now because we're now leasing an electric car, but let's just pretend that we weren't leasing an electric car. So we at my household have multiple cars. I have 3 teenagers. I didn't share that. I have 3 teenagers. So my wife and I and 3 teenagers. And for a long time we've had a Prius and a minivan. And basically we took all 5 of us in the Prius one time, the first time. Have any of you been in a car with 3 kids right next to each other in the back seat? Maybe you have been yourself. I don't know if it was good for you or not. Boy, for the parents, wow, just intolerable, right? I mean, totally intolerable experience. So now if the 5 of us are going anywhere, we take the minivan, 100% of the time. Right? 3 times the energy to move us around, 3 times the CO2 emissions to move us around, but we do it every time. Right? We can afford to pay the gas. There's no price on, a little bit of price on carbon in California. There's not a price on carbon in California that affects our behavior, given our wealth and privilege, right? So my point is, this is how you get out here, right? Is that we can avoid the psychological cost of having our kids sitting next to each other for 3 times the energy use. Right? That's how you get out here. So this is all luxury. This is all luxury consumption out here. Right? That's the difference. Everything. And these lines are. This is not an empirical analysis of where critical consumption ends and luxury consumption begins. But you can see, right, that at very low levels of energy consumption, there are huge benefits, right? Every incremental increase in energy consumption, when energy consumption is very low, there are huge benefits, fundamental well-being, not that my kids are less annoying when I spend more energy, consume more energy, but that now I'm not dying from indoor air pollution, right? Or now I'm not spending 6 hours a day fetching water. Right? Fundamental benefits, super steep curve, right? And then there's some sort of inflection point, right? And there's some scatter, but we see this inflection point around 0.1 exajoules per million people. And then after 0.2, it's saturated. We're getting a more luxurious life, but we're not getting fundamental increase in well-being. All right. So I said that we, the world, your adult lifetimes, your generation's adult lifetimes, the world will need to increase energy consumption and access. So how much would energy consumption have to increase? So if we think about, there's 7+ billion people in the world now. If we think about a world of 9 billion people living at around 0.2 exajoules per million people. So as I say, this is actually Japan's value. But you can argue maybe it's maybe there's a little bit of luxury expenditure, but definitely it's definitely everything past that is definitely not creating any increase in well-being. So let's just do the quick back of the envelope calculation. If we have 9 billion people living at 0.2 exajoules per million people, that's going to be about 2,000 exajoules per year. Anyone know what the current energy consumption globally is? I realize all the information you calculated is on the screen. Yes.
500 exajoules.
Yeah, it's about slightly less than 500 exajoules per year. Right? So, ignore climate change. Ignore adaptation to climate change. Right? Ignore the Paris Agreement. This is a big challenge, right? Increasing the total global energy supply fourfold. And not only that, like, there are reasons that, you know, I don't have to think twice about driving my minivan or my Prius or my leased electric car, right? I don't have to think twice about that, and there are 2.5 billion people cooking with biomass, right? There are reasons for that that go beyond the total energy supply, right? Access is a huge barrier, and there are huge challenges to, even if we were staying at 500 exajoules per year, right, increasing access would be a huge challenge. We're talking about a fourfold increase in total supply and solving one of those access problems. Right? Biggest challenge for your generation. Or you won't find a challenge that is more more insurmountable than that on the scale of your adult lives. That's just by itself, just the energy part. But we've got this climate change thing going on, right? So it didn't say so in the headlines of the UN Paris Agreement. How many of you have heard of the UN Paris Agreement? Did we talk about something? All right, many of you have. Excellent. So 2015, December 2015, the United Nations had their annual climate negotiations it happens every November, December, end of the year. The COP21, so that process is called the COP, Council of the Parties or something like that. So COP21 was in Paris, and the Paris Agreement was agreed. And there were lots of headlines coming out of that. Most of those headlines didn't say decarbonize the global energy system. They said keep global warming below 2 degrees Celsius above the pre-industrial baseline and pursue 1.5. We'll talk about what those thresholds mean. But in order to do that, we will need to decarbonize the global energy system. Right? So you will become familiar with this data in excruciating detail over the next few weeks. But the fundamental physics of planet Earth and other planets, right? The fundamental energy balance necessitates that in order to stabilize the global temperature at any level, greenhouse gas emissions will have to go to net zero globally. That's a fundamental physics, and like I said, that'll be a big part of the first few weeks of the course. So the Paris Agreement requires decarbonizing the energy system, and decarbonizing the energy system over basically by mid-century. So decarbonizing the energy system by 2050 gives a 50% chance of staying below 2 degrees C. And that's the number you guys will, like I said, you will be able to prove that using data. All right, so what does it, what scale of challenge would it be to decarbonize the energy system? What are the current global CO2 emissions? The number I have found most Stanford students don't know.
Parts per
Most
million.
other people don't know either. Yeah.
Are you meaning parts per million?
So the parts per million is the concentration in the atmosphere, which is another good number to know, and that's the next slide.
Yeah.
But if you know it, you can say it.
I think it's like 400.
Exactly. Yeah. So the current concentration is over 400. We're up to around 410 parts per million. And that's a result of emissions of CO2. So what are the current global emissions? This is a case where I am asking you a question that is written on the screen.
36.8.
Yes, 36.8 watts. Units are important. You don't have to know what a GT is. Yeah, okay, so GTs, now we're gonna. So there's something called the GT of CO2. All right, anyone have an inference about what a GT is? It's a gigaton. Okay. So this is a gigaton Anyone know what a gigaton is?
10 to the 9.
Alright, so giga, that's billion, very good. So we got 10 to the 9 somethings, 10 to the 9 tons. Sorry?
Shall we say 10 to the 3?
Something of 10 to the 3, yeah? So 10 to the 3 what's? 10 to the 3 kgs, exactly. So a metric ton is 10 to the 3 kilograms. I remember this because a ton, an English ton, or American ton, but I think it's called an English ton, is 2,000 pounds, right? And a kilogram is 2.2 pounds. So an American ton is like 2,200 pounds. So 2,000 kilograms. 2,000 pounds, 1,000 kilograms. Okay? So that's a lot. Actually 10 to the 3 grams, sorry.
I didn't catch that.
10 to 3 grams. Right? No? Kilograms? Now I'm confused.
Yeah, kilograms.
Kilograms. 1 kilogram is, alright, good.
Yeah.
There you go, you passed the test. Alright. It's all set up. Perfect. Alright. These are big numbers, right? It's a lot. So we're at about 37 gigatons of CO2. So 37 billion tons of CO2, or 37 times 10 to the 12 kilograms. How many grams in a kilogram? 10 to the 3, right? So that equals 10 to the 15 grams, and you'll hear petagram. That's another unit you'll hear is petagrams. So billion tons or petagrams. Look at these both. Have global CO2 emissions have we been decarbonizing the energy system over the last 15 years, 25 years? No? No one sees the decarbonization happening in these data?
Slow down.
Yeah, so maybe a little bit of slowdown. And actually the Paris Agreement was right here. And these data are from the Global Carbon Project, and I'll tell you that Rob Jackson is the current director of the Global Carbon Project. His office is at the other end of this hallway. So these data, you'll see these in the news we'll see them during the course. They usually release their projection around the COP, right? So late November or so. And Rob is the director of this project. So these numbers weren't here in Paris. This was the Paris number, and the Paris number was released the 2015 number was released at the Paris COP inside the negotiation. And it was the first year that CO2 emissions had decreased while global GDP had increased. And you can see that here really clearly, right? I mean, just like a huge decrease. Maybe not, right? So it was very slight, but there was a ton of optimism. It was a big part of the sort of final push to the negotiation was, hey, look, we're doing this, we're decarbonizing. But maybe flattening, as you say, maybe some optimism about flattening, although we have rebounded. We're back. We're on the climb. Yeah, so after 2016 was like, oh, it's a little bit up, but maybe this is still part of the flattening, right? Even when this got released in 2016. We talk about this in class every year. So we'll see last year in class we were like, oh, okay, now we're probably up. We'll see where this ends up in a couple months. We should get a release. Rob might have some insight of where it's headed. The point is we're not decarbonizing at best, we're maybe slowing down. Best case scenario, we're maybe slowing down. But this is 22, right? So decarbonization means not increasing anymore. But not increasing anymore is not enough, right? It means turning the ship around to go down, 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 down. And not just down to where we were in 1990, which you'll see a lot, in policy statements is like, or the California goal, right? Like reaching 1990 emissions by whatever year. So if we got to 1990, that seems like not the way we're headed, but if we got to 1990, how would you feel about decarbonization? 1990 levels, is that 0? No, it's like 22 billion tons of CO2. And as you know, a ton of CO2 is 10 to the 3 kilograms. So I mean, that's like off, trying to get down to 22, like down here. 0 is down here. That's 22. I don't know. 0 is like way down. It's like Al Gore. Have you seen the Inconvenient Truth? Al Gore's got his genie lift. He's got to get on the cherry picker to get all the way up to where the. You haven't seen that? That's Inconvenient Truth. It came out in 2007, which that was a while ago now. At any rate, CO2's got to go the other way. It's got to go into the floor. That's the bottom line. All right. So that seems like a big challenge, right? All by itself. Never mind increasing energy consumption, increasing energy access. Ignore all that. Decarbonize the energy system. That's the big challenge. So why the decarbonizing the energy system? Why not just let it roll? So, as Anya said, right, we're over 400 parts per million CO2 now. Is that right?
Yep.
Okay. We're over 400 parts per million CO2 now in 2018. 410 parts per million. And this is an extremely robust measurement. Okay? So this is called the Keeling curve. We'll come back to it. But these measurements started back in the 1950s. And we'll talk about the whole story of those measurements. But there is no question, if you believe in our ability to measure carbon dioxide, then there is no question that carbon dioxide concentrations are going up in the atmosphere. This is not a theory. This is not a political argument. Right? This is just that we can measure CO2 and it's going up every year. Not only is it going up in the atmosphere, but it's also going up in the ocean. And this problem was identified more recently, and Ken Caldera, you can tell I have a Stanford bias, Ken Caldera, who's here, his office is just across the street at the Carnegie Institution. He was one of the first people who really identified this ocean acidification problem. And so the partial pressure of CO2 in the surface ocean is going up right along with the atmospheric concentrations, basically equilibrated. And what do you think might happen to the pH of the surface ocean if the CO2 concentration is going up? The partial pressure is going up. The pH is going to go down, right? So if it's the ocean and the pH is going down, what would you call it? I'd call it ocean acidification too. Right? Ken called it that already. Yeah, the ocean is acidifying. Again, just if you believe that we can measure pH, then that's ocean acidification, right? It's going down exactly the rate we would expect it to go down given how much the CO2 is rising. The reason this ocean acidification is happening is that about a quarter of the CO2 that we are emitting is going into the ocean. So here's the thing about the Keeling curve. Keeling curve is only reflects about half of what we've emitted. So this really steep increase in carbon dioxide concentration, less than half of what we've emitted has actually stayed in the atmosphere. We're going to look at the numbers in greater detail in a couple weeks, but about a quarter has gone into the ocean, about a quarter has gone into the land. Vegetation and soils. All right, so this is just happening, this observed fact. Another observed fact is that the global temperature is increasing. So this is, the plot itself is from the New York Times from about a year ago, I think, that they had this figure. But the data are from NASA. Okay? So we have thermometers all over the world that go back decades, over the last 40 years or so, we've had satellite observations with weather balloons, we have ocean measurements from ships, we have floats, all these sensors that are floating around in the ocean, and they dive down, the sensors like dive down, they take measurements, they come up, they beam the data up to the satellite, they have their geolocation, their GPS location, they beam their data up to the satellite, and they go back down. So we have these three-dimensional profiles of the ocean from these Argo floats. So we have a lot of data measuring, we have a lot of measurements gathering data, instruments gathering data on temperature and other features of the climate system. So what do you notice looking at these data? This is time if the gray is too light. Time on the x-axis. Okay, increasing.
Since 1944.
Possibly exponentially. Increasing since when?
1944.
Yeah, so increasing since in the post-World War II era. But how about overall? If I said 100 years ago, how much would you say, how different is the temperature now from 100 years ago? Give or take. No decimal points, let's say. So the nearest whole degree. About a degree, right? So we've seen about a degree warming in the last century. This is global temperature. Temperature's going up. What would you call it? Global warming. There it is, right? Another measured fact. If you believe in our ability to measure temperature, then this is not a measure of, not a matter of debate, right? It's not political. There's no political statement here. There's no policy recommendation. Right? This is just, we've measured temperature for a long time. Temperature's going up. Global warming. Measure fact. All right. CO2 concentrations have gone up, right? Global temperature has gone up. Does that mean that we know what's causing global warming?
No.
No. Not. Till we get to the next slide. So scientists know, just haven't told you yet. Okay. But yeah, critically, we don't, like there's lots of things that are going up. Like number of PhDs awarded in the US is going up. Right? That's not a cause of global warming, other than that maybe they're driving their minivans. But the point being, there's lots of things that are going up. The number of petabytes of data stored globally is going up. Be producing some CO2 emissions. My point being, in correlation again does not imply causation. So we're going to talk a lot about attribution over the next couple of weeks. But essentially, we have a way to measure the CO2 in the atmosphere, the way to measure the CO2 in the ocean, we have a way to measure the temperature in different parts of the world. We don't have a way, we even have a way to measure, the effect of the rising CO2 on the radiation, like the radiative balance of the planet. Like we actually can measure the greenhouse effect. That can be measured. What we can't measure is how that, like we can't actually measure the molecules of CO2 making the thermometer measurements go up, right? We can measure the greenhouse effect, but we can't measure the response of the global climate system in a controlled way. Right? We can't run controlled experiments on the whole world. So this is, and we're going to talk about this in a lot of detail, but this is a key limitation, right? Is that we can't run experiments on the whole world. And experimentation is a key pillar of science. So, that's an actual barrier that we face. And my research group, a lot of other research groups around the world, a lot of what we spend our time on is how do we confront that barrier of not being able to run experiments on the real world. And one of the key ways is we use climate models to run the kinds of experiments that we'd like to run on the whole globe. But we can't. So we use climate models to run those experiments. So we can run, for example, using the same sets of climate models. In both cases, we can run an experiment where all of the known forcings the solar variability, the volcanoes, the carbon dioxide, the methane, the aerosols, right, where all of those are prescribed in the climate models just like we know they occurred historically. And we can use those same climate models and just remove the human forcings, right? Just say, we'll keep the CO2 as if humans never emitted any CO2, keep the aerosols as if the humans never emitted any aerosols, right? And just let the volcanoes happen, let the solar variations happen. And we can compare those two, right? So the pink is the experiment with the human forcings, the blue is the experiment without human forcings, right? And the black is the running mean of the data that I just showed you, right? So this is one of many, many, many attribution results that gives us confidence that the observed change in the climate system, in this case at the global scale for temperature, the global warming that we observe, right, is consistent with our human forcings that we know about and is not consistent with just the random variations in the climate system or changes in the solar output or volcanoes or other natural explanations. So we're going to come back to attribution as a key topic. All right, I still haven't gotten, hopefully you're not yet convinced that meeting the Paris goal requires decarbonization of the energy system. You shouldn't be convinced of that yet until you see this, okay? So you're going to become very familiar with this particular figure. We're going to spend a lot of time on this particular figure because this was a big step forward in not only in how we understand the climate system, but more importantly how the negotiations, the climate negotiations happened. Because what was observed around, I guess the first paper on this was in 2009 by Matthews et al. So this is only about in the last 10 years that it was clarified that there's this linear relationship between the total cumulative emissions of CO2 and the change in global temperature. Right? So we're at 37 billion tons per year, gigatons, yeah. 37 billion tons per year. Now, if you go back and add up all the emissions that have happened historically, that's the x-axis here, right? So we've had about 500 billion tons of carbon, or about a little less than 2,000 billion tons of CO2 total, historically, and we've had about 1 degree of warming. Right? So when you look back, the historical, we get about 1 degree of warming for every 1,800 billion tons of CO2 emitted total, right? And as long as we keep increasing the cumulative emissions, then we're going to continue to get more warming. Right? So the second big challenge I told you was decarbonizing the energy system, right? Bringing the total global emissions to net zero, right? Because as long as we're moving along this x-axis, there's some uncertainty about what the exact slope of this relationship is, but it is a linear relationship with cumulative emissions. So we can expect that as long as we're still a net global emitter to the atmosphere, we can expect continued warming. Okay, and this has, we'll talk about this in more detail because it has a lot to do with the total lifetime of greenhouse gases in the atmosphere. And you're going to spend a lot of time towards the middle and end of the course looking at different budgets, real budgets, such as those in the UN Paris Agreement. All right, so why, so that's why I say that one of the grand challenges is decarbonizing the energy system, right? Meeting the Paris goals, stabilizing the climate system. That requires net zero emissions. What's the scale of that challenge? Right? We calculated back the envelope the scale of the energy challenge at a 4-fold increase in global energy. So we're going to look real quick at some data on our current energy system. So before we do that, I'd like you guys to make a prediction. I'd like you to predict the the fraction of total energy supply that comes from fossil fuels. So go ahead and talk amongst yourselves for 60 seconds, and then you're going to come back with a prediction of the percent of total energy globally, total global energy from fossil fuels. And remember, that's about 500 exajoules of energy supplied per year. So what percent of that 500 exajoules per year is from fossil fuels? Go.
Yeah.
I was gonna say 62.
I think it's definitely higher than that.
What did you say?
Like 13. So it's
Like, I think
Nuclear is the other big one.
I think
And then, like renewables and stuff.
Yeah.
Pretty good.
and it's like really active, like the countries that are
That's
like
right.
green, probably
Well,
using a lot of like energy, like
I feel like it's on the board of like no.
So like,
our consumption.
Well, no, that doesn't, you don't have like,
Yeah, if we're looking
gas.
at
no, like,
like
yeah, that's.
how they said it.
what is
I mean,
it?
you're
Cost?
I don't.
I think 75.
I feel like it's like,
I feel like
the
it's
percent of
renewable.
renewable
Yeah.
energy is
Yeah.
higher than I expected.
Anything
to
that's
be,
Yeah.
like old.
But by that I'm like 30.
This is just like 90.
Really?
All right, take 10 seconds.
Well, I could be smart.
10 seconons to
I think it's
solidify your prediction.
Oh, you switched it out?
I think it might even be higher.
60 to 60.
I'm still thinking 60, but like, I just don't have the gauge.
All right. Who wants to offer a prediction? Sean.
85.
Y'all have to agree at your table.
90.
70.
No, I don't want to say it.
Anyone else? All right.
13%.
So here's the energy pie around 2014. Right, so if you add up coal, oil, natural gas, you get about 85%. And so 13% from quote, renewable energy, 2% from nuclear energy, the remainder being fossil fuels. So that 85% of our current energy supply of about 500 exajoules per year is from fossil fuels, right, that emits CO2 to the atmosphere when it is combusted. Of that 15% that's not from fossil fuels, 10% is from biomass. And what do you know about biomass burning?
Like, it also releases.
A lot of particulate matter and releases CO2, right? So the one sort of maybe it's releasing CO2 that used to be in the atmosphere relatively recently. The plants maybe that's a net zero, although it's not always. But a lot of air pollution. The point is, most of what's not fossil fuels is still really polluting. That's the point, right? So we're not like in terms of clean energy. Globally, we are mostly not doing it, right? Mostly not doing it. So. Again, stabilizing the global temperature at any level requires net zero carbon emissions. Definitely 85% of the current 500 exajoules is CO2 emitting. And we can have a discussion about the biomass as well, but the biomass isn't going to make that any less in reality. So now we've just gotten through our, for our first two big challenges, what have I told you? Fourfold increase in total energy, while at the same time increasing access and removing 85% of the current energy. Feeling optimistic? Yes! I knew it! It only took till day 2. It often takes till day 3. But this year it only took till day 2. Alright. And we're not even done with day 2. We've got 11 minutes left. Yes. Yes. This class is really depressing. But this is the optimistic part. This is the most optimistic data. Alright, so we're only 2 challenges down. We still got the 3rd challenge, which is adapt to continued climate change. And this should be an easy, well, I mean, this is not controversial. And just to give you the punchline right away, how much global warming have we already had?
1 degree.
1 degree. What's the Paris Agreement say?
No more than 2.
No more than 2, and pursuing 1.5, and that requires decarbonizing the whole energy system. But even if all of that happens, right? Even if the whole total remaking of the global energy system happens, that's still more global warming than we've already had, right? So this should not be a controversial concept. That we are. I get this question frequently. Oh, so are we going to have more global warming? It's, well, even if like the most extreme climate policy gets enacted, that's still baking in more global warming. Right? The best case scenario is that we have more global warming. The worst case scenario is that we have more than that. So we are going to have to adapt to continuing climate change. We're already experiencing impacts from 1 degree. So if we get 1.5 or 2 or 3 or 4, we're going to have more than we've had now. That's the short version. But since we have 9 minutes left. So one, not universal, not comprehensive, but important indicator of those impacts is severe heat, and this is one of many measures. So these 2 maps compare the fraction of seasons, so in this case it's June, July, and August, but we've published, the paper has all the seasons. The fraction of seasons that are hotter than what happened during the late 20th century. Okay, so we can look at 2 degrees of global warming, like the Paris Agreement's targeted. We can look at 4 degrees of global warming, which is the trajectory we've been on. What do you notice about these 2 maps?
Variation.
Okay, they're different. Is one of them more or less red?
Yeah.
Alright, that's all I'm asking. Yeah, one of them's really red. What does really red mean? It means really hot because we were careful about the color bar that we used. Yeah, really hot. In fact, I mean red, this is 80% or more. Anywhere you see red on the screen is 80% or more of, we're looking at the northern hemisphere, let's look at the US, right? 80% or more of the summers are hotter than the hottest summer that happened in the late 20th century. Right? So all of that climate variation that we've been accustomed to recently, anywhere from 75 to 100% of the summers exceed that record, that former record, at 4 degrees of global warming. So what about 2? Paris target, right? Avoiding the worst impacts, in quotes. What is that? What do the colors tell you about 2 degrees? That's okay.
At lower latitudes, I guess it's still going to be 80% or higher.
Yeah, you see a lot of red at lower latitudes, right? A lot of red at lower latitudes. So again, 80, 90, 100% of years exceeding the record hot year at 2 degrees of warming. And we even, in another paper, we took this a step further and we said, at what point will every year be hotter than the record hot year? And in fact, it is the low latitudes that show the most robust emergence of that, what do we call it, permanent emergence of record-setting heat. The words we use in the title of the paper. So why do you think the lower latitudes show that? Sean?
Is there equatorial regions?
There are equatorial regions by definition since they're lower latitude.
So
And what about equatorial regions?
So they're getting more direct, like radiation from the sun, and like global warming. The idea is that it's kind of like insulating our atmosphere. So because it's more direct, it's then held there, and so those regions are more vulnerable to.
Okay, so this does have to do with the direct sunlight or the tilt of the Earth. That's right. And there's something in particular about the tropics that makes, in this measure, makes them emerge much more quickly. Yeah.
Maybe like the wind patterns?
Yeah, so for the climate dynamics that are associated with that are, yeah, the wind patterns are important, the circulation, the atmospheric circulation, but there's something that's even simpler about why it is that less warming makes more exceedance of the record.
You just want humidity?
So the humidity has to do is important for the temperature change, correct? So these are all really important climate dynamics questions, and I'm like, we can get even simpler. It's like simple, basic, not even statistics, just basic counting. Yeah, James.
Would it be because of the population, that is the region that experiences higher population growth rate?
Yeah, so that's a correlation. That is correlated. And population and poverty, that is not cause. So I'm going to give you guys a little help here. So think about how much the temperature varies from season to season in different parts of the world. It varies from year to year in different parts of the world. Now, when you think about it without raising your hand. All right, now that you've thought about it, I think you've talked to somebody. Think about the variation in temperature in different parts of the world. Does that help to explain why the lower latitudes have a stronger emergence of record-setting heat at a lower level of global warming? Go. Here you talk.
You're not experiencing like huge shifts between like seasonal.
Yeah, so maybe like in places where it's winter, there could be more extreme winters,
Right.
slows the average down.
So maybe if it's everything heating up, it's
It's like
all
things a little hotter, it's easier.
Yeah, this is in the mat. Yeah, what you're trying to say? Like,
Yeah.
Okay. So it's like,
All right, anyone got an explanation? Sarah, I heard you saying something.
Oh, yes, so we said that because those areas that are closer to the equator experience less season variation, they're going to be continuously experiencing the effects of like the greenhouse effect, whereas places with winter, if there's like a more extreme winter, then that can help bring the average temperature down.
Yes, so that at the heart is the answer. The whole world's experiencing the greenhouse effect, so that's have some nuance and the humidity that was mentioned earlier matters, the water vapor feedback matters. But at its heart, this is just simple variation, right? Simple, not even statistics, just counting. So if we're up here at, if you think about 45 degrees north, and it's not just the seasonal variation, but also the interannual variation, right? So basically the higher in latitude you go to the north or south, the more variation there's going to be not only throughout the season, but also from year to year. And if we go down the lower in latitude you go, so if you go to the equator, not only is there a lot less variation between summer and winter, right? It's a lot less seasonal, it gets warm throughout the year basically at the equator, but there's also less variation from year to year. So the temperature is a lot more steady from year to year, right? So if this is temperature and this is time, if I showed you these two, which one would need more warming to permanently exceed the record temperature? Always be above the record temperature. Yeah, the higher one is going to need a lot more warming, right? You're going to have to shift this, right? You're going to have to, if this is the mean, right, you're basically going to have to shift this distribution all the way up, right, so that this low is above this high. You're going to need, right, you need that much warming to get the lowest point permanently outside of the highest point. Down here, where there's less variability, right, you're only going to need this much warming to shift outside of that variability. So that's fundamentally why the lower latitudes, even though they have actually had less magnitude warming historically, and why they are projected to have less magnitude warming at 2 degrees or 4 degrees Celsius, they're actually much more exposed to unprecedented heat because the variability is a lot lower. And we'll come back to this a little later. All right, and the last, I want to not give sea ice a short shrift. So in the last 10 seconds, we'll come back to this as well. Another big impact, not only potentially, but also that we're already experiencing and living with, is sea level rise. Right? And historically, most of the sea level rise that has happened has been from the thermal expansion of the water, right? As the water has warmed up, it occupies more volume. But we're now also seeing substantial contributions from land ice, right? So water that is not in the ocean, it's locked up on land, and as it melts, as that ice melts, that water runs into the ocean, right? And so Ken Caldera, again, across the street, his group has done this work. Ricardo Winkleman is the first author on this, where they looked at the different cumulative emissions, like I showed you on that other plot, and how much of Antarctica would be lost from melting for different levels of cumulative emissions, right? So the Paris target is another, we've had 500 gigatons of carbon emissions so far. The Paris target is something like another 500. What has actually been committed in the Paris Agreement is 1,000 gigatons of carbon, and or 3,500 gigatons of CO2. All of the brown are areas that have lost ice, right? So there is a big difference between what the world has committed to doing and what the world has set its goal is. What we're going to talk a lot about in the class is kind of what are the differences in impacts between these different levels of emissions, and what are the different kinds of policy solutions and technological solutions that people have proposed to try to achieve the targets rather than the commitments. All right, we're past time, so I will I'll post this on the canvas. You can take a look at it, and otherwise I will see you all on Tuesday.